Any questions? Fine. If you don't have questions, then let me proceed further. Yeah, so what is that we were doing? Yeah, so we had what is known as the Lebesgue outer measure. M star, the so-called Lebesgue outer measure. Right. So first thing that we saw is that, well, we had some simple properties, that then the main thing is that M star is countably subadditive. Yes. But M star is not countably additive. So at most that you can expect is only subadditivity and not countable additivity. This much we saw, right? And therefore, to overcome this, we defined what are known as Lebesgue measurable sets. In fact, so for any, so E sets, so this collection we called it as, we wrote it as scriptium. So E belongs to scriptium if and only if M star of A should be same as M star of A intersection with E plus M star of A intersection with E complement for any E subset of R. Yes. Sorry, A subset of R. Yeah, this is how we define. One of the major things that we saw is the following. What is that? Yes, so the first thing is that M star of union 1 to N EI is summation 1 to N M star of EI whenever EI belongs to M for all 1 less than or equal to I less than or equal to N. Yes. Yes, so this is one of the major things that we saw. Yeah, so yeah, in the last class we were proving something. First thing. And then second thing is that the script M is closed under taking finite union. Yeah, so in the last class, I think, although I have posted the PDF of this, but there is a, yeah, so thanks to Stay. So he pointed out that there was a gap in the proof and it was not recorded. So let me repeat the proof once again. So as usual, we'll prove this only for n equal to 2. So let E and E comma F belong to M. So we'll have to show that E union F belongs to M. So let A subset of R and then so first thing is that, so note that A intersection with E union E1 union, sorry, E union F. This I can write it as, yeah, so this E union F I can write it as E union, sorry, E complement intersection with F. Yes, so this is what I want, right? And therefore this I can write it as A intersection with E union with A intersection with E complement intersection with F. Yes. Yeah, this is the main thing that I wanted. And therefore, this will imply that using the subadditivity, E union F, this is going to be less than or equal to M star of A intersection with E, because these two are disjoint. We have written E union F as a disjoint union. Although they are disjoint, you have written it as two union, and using the fact that M star is subadditive, this is less than or equal to M star of A intersection E plus M star of A intersection E complement intersection with F, right? And therefore, M star of A, this is what we wanted, which I can write it as M star of, yeah, so now let me use the fact that E is measurable, therefore I can write it as A intersection with E plus M star of A intersection with E complement, because E is measurable or E belongs to M. Right. So let me call this as 1. Fine. Now, what am I going to do? So let me write the other one. What is that I wanted? Now, A intersection with E complement, I have the other set, and therefore this I can write it as M star of A intersection with E plus M star of A intersection with E complement intersection with F plus M star of A intersection with E complement intersection with F complement, right? Since F belongs to M. Yes. Now, so I have, so these two sets, the first two, this will give me greater than or equal to M star of A intersection with E union F plus M star of A intersection with E union F complement by 1. Yes, so we now here is the place where we have used 1, right? And that's exactly what we wanted to prove. So in fact, so in the definition, you can notice that this much is, so in fact, less than or equal to is always true in this equality. Less than or equal to is always true. What we wanted is only the other way, greater than or equal to, and that's what we have shown. Right. So thus, E union F is Lebesgue measurable. Yes. Yeah, a good exercise here is that if E1 and E2, if both belong to M, then show that E1 minus E2 belongs to M. Prakash, you want to have any question?
सर ये ऊपर पार्ट समझ में नहीं आ रहा है बाय वन जो लिखा गया है
दोबारा बताओ, कौन सा समझ में नहीं आ रहा है?
लिखा गया कि m स्टार ए ग्रेटर देन इक्वल टू m स्टार ए इंटरसेक्शन, ये लेबेग्यू मेजरेबल कैसे होगा? इक्वल टू होने से होगा ना?
हाँ, मैं यही कह रहा हूं कि इसमें तो लेसर इक्वल हमेशा होगा।
हाँ
सबएडिटिविटी के कारण इसमें तो लेस देन इक्वल टू हमेशा होते ही रहेगा, उसमें तो दिक्कत नहीं है।
हाँ
क्योंकि
सर
हम
समझ गए।
ये जो ये है ना, इसको हमेशा ऐसा लिख सकते हैं, ये इंटरसेक्शन ई यूनियन विद ये इंटरसेक्शन विद ई कॉम्प्लीमेंट, ये तो हमेशा ट्रू है।
यस सर,
Therefore,
यस सर।
m star of a is always less than or equal to m star of a intersection with e plus m star of a intersection with e complement, ये तो हमेशा ट्रू है। इसलिए एक तरफ का प्रूफ तो हो गया, करने का जरूरी नहीं है। Therefore, to prove only the other way. ठीक है?
ओके सर।
Right. Yeah, there is a small change. Maybe I'll call this as 2. First one is that if E1 comma E2 belongs to M, then show that E1 intersection E2 belongs to M. So once you prove one, then 2 follows from that. Well, even without this you can prove, but still. Right. Yes, so now, yeah, so next lemma is that let E1, E2, En be a disjoint family from, in fact, a finite disjoint family from M, then for any A subset of R, M star of A intersection with union 1 to N EK is equal to summation 1 to N M star of A intersection with EK. The proof is quite easy. We have almost done all the things, so I'm just leaving it as an exercise. Right, so here is the final lemma that we wanted, or the final theorem. Yes. The class of all Lebesgue measurable sets is closed under taking countable union. That is, if En n in n is a countable family of Lebesgue measurable sets, then union over n in n, En belongs to M. Yeah, so one thing that I wanted to say is that there are 3 words. One is family, The other one is class. Third one is collection. Yeah, so I'll be using them with the same meaning, although they have got difference. There is a slight difference in each one of them, but still, I don't mind. So throughout the course, I'll be using these three terms again and again with the same meaning. That's what I wanted to say. Family, class, collection, they differ actually. Right. So let's now get into the proof. Yeah. So now proof is not difficult, but let me call E as union over K in N EK. Right. So we'll have to show that this E is a Lebesgue measurable set. So let A subset of R. Now, yeah, so this is one of the important constructions that we are going to see. So let me call A1 as E1 and then AN as En minus union K running from 1 to N minus 1 EK. And the last set is capital F, which is union K running from 1 to N AK. Yes. Sorry, this should be Fn. This is for N in N. And this is for N bigger than or equal to 2. Yes. Right. Fine. Right. So now, what can you say about ANs?
Disjoint.
Yes, exactly right. They are disjoint, and then they are in fact pairwise disjoint. AI intersection with AJ is empty whenever I not equal to J. Yes, first thing. Second,
They are Lebesgue measurable sets.
why is it Lebesgue measurable?
Because En is Lebesgue measurable and finite union of Lebesgue measurable sets is measurable, and in last exercise we have seen that if two En and union K running from 1 to N minus 1 EK both are Lebesgue measurable, their difference En
Exactly.
minus this will be also.
Yes, so first thing that you'll have to observe is that ANs are Lebesgue measurable. ANs are Lebesgue measurable. Yes. Sorry, for all N in N. For all N in N, ANs are Lebesgue measurable, right? And then second thing is that ANs are pairwise disjoint. Yes. Not only that, they are pairwise disjoint and yes. So what will be the union? Although we have called it as
FN.
Fn. Huh?
FN.
Well, we have called it as Fn, that's right, but something more in terms of EKs?
Union K running from 1 to n En. I mean K. Oh.
So what have we done? That is the whole point that you'll have to observe. If you have a collection, you can write it as a disjoint union without losing the union. Right? We have not lost elements of this union, but you have written it as disjoint, pairwise disjoint collection. This is the main thing that you'll have to understand. Yeah, this is one of the ideas that we are going to use in many places.
Sir.
Huh.
Sir, if E intersects F belong to M, then can we say E and F both belong to M?
Can you repeat? If E and
E intersection F. वो E intersection F अगर M में से belong करता है सर, लेबेग मेजरेबल है.
E intersection F.
हाँ तो सर क्या हम कह सकते हैं कि E और F both belong करेंगे M में से?
नहीं, ये नहीं कह सकता. That this need not be true.
Okay sir, okay.
Right. These are pairwise disjoint. Fine. Therefore, now, so we have, therefore, M star of A intersection with Fn, which by definition is M star of A intersection with union 1 to N AK. But this is same as M star of A intersection with union 1 to N EK. Yeah, just now we proved something, or I have left it as an exercise. Just use the previous lemma. Then, sorry, this is going to be because, no, I don't want, all right, this is going to be summation 1 to N M star of A intersection with EK, right? No, these are not EKs. I want only because there you need disjoint family, right? So I cannot use this here. So what I needed is only AK, right? So I'll have to use only AKs. Yeah, this will be same as summation 1 to N M star of A intersection with AK. Right. This is from the previous lemma. So let me call this as 1. Now, second thing. Yeah, so if you use this observation that the union 1 to N AN is equal to union 1 to N EK. So Fn is equal to union K running from 1 to N AK, which is same as union K running from 1 to N EK, which is contained in union K running from 1 to infinity EK, which is E for all n in n. And this is true for all n, right? So each Fn is contained in E. And therefore, E complement is contained in Fn complement for all n in n. And therefore, by the monotonicity of M star of E complement is less than or equal to M star of Fn complement for all n in n. So let me call this as 2. Yes, so now I have 2 equations which I'm going to use. Yes. Now, each AK belongs to script M and therefore Fn belongs to script M. Yes, so now Fn belongs to script M and we are chosen an A subset of R. And therefore, M star of A, because Fn is a Lebesgue measurable set, this is same as M star of A intersection with Fn plus M star of A intersection with Fn complement, which is equal to, yes, so now M star of A intersection with Fn is same as summation 1 to n M star of A intersection with AK, right, plus I'll have the other part, M star of A intersection with Fn complement, right. This is what I have for the time being. Now this is M star of Fn complement. Yeah, so this follows from 1. Now by 2, this is going to be bigger than or equal to summation 1 to n M star of A intersection with AK plus M star of A intersection with E complement by 2. Right. Fine. Right. So now this is true for all n in n. Right. So since this is true for all n in n, true for all n in n, letting n tend to infinity as usual. What do we get? We get M star of A bigger than or equal to summation over n in n M star of A intersection with AK plus M star of A intersection with E complement, right? Now, AKs, they all are disjoint and therefore, in fact, so you will have it as summation over n in n, sorry, you will simply have it as, yeah, in fact, so you don't even need that, in fact, you don't even need the equality here. So just a greater than or equal to will suffice for us. M star of the union over n in n, A intersection with AK plus M star of A intersection with E complement, right? Now this part is going to be M star of A intersection with union over n in n AK plus M star of A intersection with E complement. What is this union? Union over n and ak.
E.
E. That's it. And that's exactly what we wanted. That's it. Done. We are done. Right? M star of A is bigger than or equal to M star of A intersection E plus M star of A intersection E complement, where E is the union. Yes, so that's what we have chosen initially, right? And we are done with what we want. Right. So here is the theorem that answers the question raised by Sneh. That's what he asked last time. Do we have a non-trivial example of a Lebesgue measurable set other than the whole of R and empty? Yes, in fact, we have a large class. For any A in R, the interval A comma infinity is Lebesgue measurable. Yes. Proof. Yes. So let A belong to R, fix an A in R, and then let me choose E as A comma infinity. Right. So we'll have to show that this E is Lebesgue measurable. For this, as usual, let's begin with an A subset of R. Right. So our idea, as usual, is to use the epsilon. Let epsilon greater than 0. Correct. Now I have a subset of R and an epsilon positive. So by definition of definition of M star, there exists a countable family or a collection In of open intervals such that A is contained in the union and summation over n in n length of In is less than or equal to M star of A plus epsilon. Right. So this we are going to use. Yes. Now note that A intersection with E. So E is the interval which is contained in union over n in n In, right, intersection with E. So same as union over n in n In intersection with E, right, and A intersection with E complement, which is again union over n in n In intersection with E complement, which is union over n in n. Well, let me write one more even. In intersection with E complement. Well, here you will notice that this is n intersection with A comma infinity. Minus infinity comma close to E. Right. Yeah, so the first thing that to be observed, observe that intersection of any two intervals is again an interval. If you have two intersections, two intervals, their intersection is again an interval. That's the main thing that you'll have to observe. And therefore, this whatever we have here, this is an interval, and this one is also an interval. So let me call in dash as in intersection a comma infinity, and in double dash as in intersection with minus infinity comma a. Yes. Yes. So with all these observations and all those, now let's proceed. M star of A intersection with E plus M star of A intersection with E complement. So we'll have to show that this is going to be less than or equal to M star of A. Yes. So what are we going to show? We are going to show that this is going to be less than M star of A plus epsilon. Right. Yes. So first thing, this is less than or equal to. We have already shown something. What is that? Yes. So A intersection E is contained in this union. So this is less than or equal to summation over n in n. Sorry. Yeah. So let me add one more before I proceed. Less than or equal to M star of the union. This is in dash plus the other one is M star of the union of in double dash. Right. Now, which is again less than or equal to, use the countable subadditivity, summation over n in n, M star of in dash, again here, summation over n in n, M star of in double dash, right? Yes, so now in dash, it is an interval, and therefore, and in double dash, it's again an interval, and we know that Lebesgue outer measure of an interval coincides with the length of the interval. Therefore, this is same as summation over n in n, length of in dash plus maybe I don't even need this part immediately. Yeah. Yes. So first thing, let me put them together and then we'll see. M star of in dash plus M star of in double dash. Yes. So first thing is that in dash and in double dash, these two are disjoint. That's the first thing that you'll have to observe, because in dash is in intersection with a k comma infinity, while in double dash is in intersection with the complement. Yes. So well, we do not know whether, well, yeah. So we do not know whether they are, well, so the only thing is that, well, right. So this is same as summation over n in n, sorry, length of in dash plus length of in double dash. Yeah, they are disjoint intervals. What is the length of the two disjoint intervals?
Length of their union.
Length of the union. But what is IN dash union IN double dash?
IN.
IN. But how did we choose these INs? Yes, so this is how we have chosen. Summation over n in n, length of IN is less than or equal to m star of A plus epsilon. That's it. This was our choice. That's it, done. Right? So since epsilon greater than 0 is arbitrary, it follows that m star of A intersection with E plus m star of A intersection with E complement is less than or equal to m star of A. That's it, done. That is E, which is A, open A, comma, open infinity is Lebesgue measurable. Yes. So here is the, yeah, so maybe I'll put it as a corollary, but then proof is an exercise. Having done all these things, I think by now it should be clear. Every interval is Lebesgue measurable. Every interval, whatever be that interval, finite or infinite, doesn't matter. Proof, it's a good exercise. That's it. So with this, the syllabus for Lebesgue measure, whatever I wanted to do, is over. Yes. Yeah, so let me also post this, whatever I wanted to say now. I'll also post this in the Telegram. But let me inform you all that there will be a quiz in the coming week. Today I am planning to finish this Riemann integration part. So that is the tutorial part, so that next week we can have a quiz. So fix a date and then tell me. Monday to Friday, fix a date, time, not during the classes. And not on, especially not on Mondays and Thursdays between 3:30 to 5, because I have a class on Mondays and Thursdays between 3:30 to 5. I don't know why others don't want to attend the class. I'm not sure. Only 32 are attending, but anyhow, doesn't matter. Yes, so if you have any questions, I'll be happy to answer, or else I'll have to move to the next topic.
सर क्विज में सिलेबस कहाँ तक आएगा पूरा?
हाँ, so it's only Riemann integration, purely Riemann integration.
Okay, sir.
The syllabus for quiz 1 will be Riemann integration. It is just Riemann integration. Prepare well. Score well.
क्विज होगा सर?
हाँ,
कितने देर का टाइम?
कितने देर का है टाइमिंग? 15 minutes, 15 to 20 minutes. Well, 20 minutes for writing, 10 minutes for scanning and uploading. Not more than that. I think that should be fine, right?
And sir, how many questions can we expect?
At most 2. At least 1, at most 2. Not more than that. So all the instructions, blah, 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 whatever you wanted, all these will be uploaded in the Telegram. Whatever I wanted to, I'll do everything through Telegram.
And sir, how the exam will be conducted through Telegram only?
So the exam will be conducted through MS Teams. There will be 3 to 4 groups. Each one will be in the vicinity of some PA or research scholar. And then you will have to submit the quiz copy or whatever copy it is, whether it is quiz or minor or major, anything that it may be, you will have to submit it through Telegram, not in this common portal, but rather through your personal chat. So if it is Sneh should submit only through his personal chat, not in this Telegram group, measure integration group. So if the exam say starts at 10 o'clock and if you are supposed to finish it by 10:30, you can start submitting only after 10:25. So you submit your paper only after 10:25. Make sure that you have written your name, entry number. That's it, these two. So once you have written these two, then I'll just download them, I'll correct it, and then again post it only in your personal things, not in others. Fine, is that clear for all?
Sir, where we got the question paper?
Same Telegram.
Okay, sir.
If the exam starts at 10, the question paper will be sent to you 2 minutes before. It is not a lengthy file. It is not going to be of several GBs. It is going to be just some 10 KB, maximum 50 KB, not more than that. I understand that many of you don't have a proper internet connection. There can be several hindrances, oppositions for internet. So many things are there. I understand, but we are in a critical situation. So we are forced to. Mostly what I upload is going to be the simplest one. My question papers are always simple, easy, but prepare well. Never ever think about copying. Please. Do not think about copying.
And sir, this how many marks this quiz will contribute in our final?
10 marks.
Okay.
I think this we have already discussed in the first lecture, right? Yes. So here it is. Minor 1 20, minor 2 20, quiz 1, quiz 2, quiz 3, each one for 10 marks. Major will be for 30 marks. All 3 quizzes are compulsory.
Sir, extend also the notion of Lebesgue measurable sets on R2, R3 as well.
Yes, of course, even in Rn. Replace these open intervals by open cubes, n-dimensional cubes. Then you should be able to. So you write it as well. I'll simply write it as well. For any E subset of Rn, M star of E is infimum over sum of n in n volume of, what should I write, cubes, n-dimensional cubes, Cn, such that Cn is contained in union over n in n. Sorry, I am not supposed to use n again because I already have an n there. Over k in n, ck, k in n, sorry, I should write it as E is contained in ck, where ck's are open cubes. That is, ck is given by product I running from 1 to k. Sorry, not k, this is n. N, ai, well, all these depends on k, therefore this is an open interval. This is an open interval. Yeah. So this is by an open cube, I mean, I'm only drawing it for, well, you don't need cuboids, right? You don't even need cubes, cuboids. What I'm drawing is only for 3-dimensional, n-dimensional you should be able to view. Yes, so I have returned this. This you can write it as the product of 3 intervals. That is A1, B1 cross A2, B2 cross A3, B3. Yes. So that's exactly what I've done. You should be able to write it as union of these things. Take the volume. This is the n-dimensional volume.
Sir,
Huh?
can we replace cubes by spheres and get an equivalent condition?
Yes, of course. And both are equivalent. In fact,
Yes.
equal. You can even replace cubes by spheres and get the same answer.
And in the same spirit, can I replace cube by any convex solid?
Convex solid.
Like ellipsoid.
Yes, ellipsoid, it should be possible. Yes. I think it should be possible. I haven't tried, but sphere, I'm 100% sure.
Okay, sir.
Yeah, with the sphere, it is possible. Yes. Ellipsoid, I think it should be possible. It should be. It should work. It should help us because
They are basically the
spheres
same
are
matrix.
special examples of ellipsoids.
Yes, sir.
Spheres are special examples of ellipsoids. So if I choose A equal to B equal to C, then what I get is the sphere. Therefore, it should be possible. Yes, it is possible. Right. You are right. Thank you.
Okay.
But general convex bodies, convex solids, I'm not sure. Yeah, in fact, there is a whole subject on this, what is known as geometric measure theory.
Okay, sir.
Which contains lots of details about all these.
Thank you, sir.
Yeah. Any other questions? So that if you don't have, then we'll break for 10 minutes and then we can start our tube.
So please give some examples of non-measurable Lebesgue sets.
Can you repeat? Sorry.
So, please give some examples which are not Lebesgue measurable.
Oh, I think you haven't understood this part. Where is it? This one. Yeah, so if they are going to be measurable, then what does it tell us? That then it is going to be, so you are supposed to have the what? Equality, but that is not the case. That's the whole point here. Is that clear? For example, this E itself, whatever we have constructed, this, not this E, sorry, this collection, this is, they are not going to be Lebesgue measurable, this collection, En. This collection, it's not a Lebesgue measurable collection. That's the main thing here. Yeah, so in fact, so that's the point that we have used again and again. Yeah, so this we again observed. You get a pair of subsets such that they are disjoint and there is a strict inequality. So if every subset is Lebesgue measurable, then you are supposed to have equality, but that's not the case. Which means even if one of them is Lebesgue measurable, then you are true, you are done. But that is not the case. There are subsets which are not Lebesgue measurable. Well, if you assume the so-called axiom of choice, then everything falls into what I'm saying. But well, why should I believe axiom of choice? In what sense it is true? Does there exist a proof? It's only an axiom. If you keep asking this kind of questions, then it is only a myth. That it's only beliefs. Right? So you don't have to believe in axiom of choice. If you don't believe in axiom of choice, then that does not exist. It may not exist in general if you don't believe in axiom of choice. It's only how much you believe in axiom of choice, and therefore in so-called Zorn's lemma. Yeah, this you must have done in your real analysis. Axiom of choice, Zorn's lemma, continuum hypothesis.
So, is cross product of two non-Lebesgue measurable sets is again non-Lebesgue measurable set in R2 or Rn?
I think it is not measurable there. I think it is not. But I think it is not. Yes. Yes, it is not. But how should I give a proof? Proof. Yeah, proof should not be difficult, huh? I think once we do the abstract theory, we should be able to. There we should be able to say a lot. Especially when we do towards the end, when we do so-called product measures, Fubini's theorem, there we should be able to say a lot. In those contexts, we should be able to say. That's the thing. Right. Any other questions? If you don't have, then let me stop.
Sir,
Thank you. Yes. Yes, please.
yes, sir.
Sir,
Subset of measurable set is also measurable.
That need not be. Not all subsets. For example, the whole R itself is measurable, but there are examples. That's what we saw. There are examples of non-measurable sets. Right, so let me stop here. We'll meet at 10:10. Thank you all.
Thank you, sir.
Thank you, sir.